Okay, we're going to talk about the analysis criterion of the internal assessment. So, analysis is really what you should think about in terms of your data, the processing, and the uncertainty. I'm going to look at each strand, mainly focusing on the 5-6 level, since that's what we're all shooting for, and try to just decipher what the language means to tell you what you need to do to earn high marks in analysis. So, 5-6, the report includes sufficient relevant quantitative and qualitative raw data that could support a detailed and valid conclusion to the research question. So the key things that you should take away from that is that you need to have sufficient data. That means enough data. So that means you don't get one trial or even two trials of data and then call it as good. You get as much data as you possibly can within the IA lab periods. So this one, as much as anything else, is has to do with your effort during the lab days and your commitment to getting enough data. It's especially important for databases, a database lab. For a database lab, you need lots and lots and lots of data. That's that you get around the fact that you don't have to actually design an experiment and carry it out in the lab. All that part has been removed for you. So sort of the replacement is that you need to look at lots and lots of data to make it a valid database lab. And you're going to lose marks here if you don't collect data from that many sources. So first of all, you need to have enough data in terms of enough trials, enough different values like independent variable values or samples being tested. It also says qualitative raw data, which means observations. Something really easy to overlook, but observations. What did you see, smell, etc. about your lab? Now, obviously, if you do a database lab, then you don't need to record observations. It's not really relevant. But if you do a lab that involves any sort of chemical reaction or color change, include some descriptions about what you saw, especially if there's anything that stands out about particular trials. It's really important to include some observations because you can connect it in with maybe evaluation comments later on. But that's strand one, raw data. Now, it doesn't really specify in the strands that it needs to be raw data, but I would encourage you to always include raw data first before doing any processing, which means if you're doing a titration, always include both the initial and the final volumes before you do the change in volumes, things like that. Even simple calculations, always show your raw data first. Okay, strand two is processing. Appropriate and sufficient data processing is carried out with the accuracy required to enable a conclusion to the research question to be drawn that is fully consistent with the experimental data. So this just means, if you planned on calculating activation energy or you planned on calculating concentration of something, that you've actually carried out all of the processing to do that. So this is where you're going to get graded on your calculations. So that's your data processing calculations. Also, any graphing that you've done. So graphing, which includes adding trend lines to graphing. And this is where you're really going to get graded on the accuracy and the completeness of these things, of X, Y, and Z. So I'll just leave of the things up above: calculations, graphs, trend lines, things like that. So it's got to be carried out with accuracy. If you make mistakes, then you're going to get knocked down. And it has to be thorough, actually getting to what you set out to calculate in the research question, not coming up short and just finding something else to look at instead of the value that you said that you would calculate. You should always just show one sample calculation. You don't need to show any more than that. It's just a waste of paper and your time for typing it all out. But always show the math. Don't just describe what you're doing in words. It's probably better to show the equation that you're using with a brief explanation and then actually show yourself working through the mathematical steps. And try to use equation editor or something like that when you do these calculations. It makes it extremely much neater if you can do that. Now, the neatness of the calculations is actually going to get graded in communication, as is the neatness and the labeling of your data table, which is why I haven't really discussed those during this video. Uncertainty. The report shows evidence of full and appropriate consideration of the impact of measurement uncertainty on the analysis. So this means that you're recording and reporting uncertainty with your raw data. and you are propagating uncertainty with your calculations. If you're calculating an average, then you're determining an uncertainty on your average values. Usually it's that sort of half the range. Rough way to come up with uncertainty based on all of your different trials, half the range, or the biggest difference between average and max min values. That's a way to come up with it. So full consideration means you started off with uncertainties from your equipment with your raw data, you've propagated it through with any calculations, and you've come up with uncertainty values on any average values. And then continuing on from that, any final calculated values should be presented with uncertainty values, with their uncertainty values. Don't forget to round to match the uncertainty. Also, if you're going to do a graph, I would strongly encourage you to add error bars to match uncertainty. And if you add a trend line, like a linear trend line, and you really want to impress them, then you should add max and min lines of best fit, which match the uncertainty range. Now that's a bit more advanced, something you'd probably do more likely in a physics course that's a bit more quantitative. And if you're concerned about that, you can always ask me for help with it. I'm not going to go over it in this video. Lastly, strand 4 is interpretation. The process data is correctly interpreted so that a completely valid and detailed conclusion to the research question can be drawn or deduced. So in this part, you're actually with words interpreting the data. Now, there's a lot of overlap with this strand and evaluation, which comes next, drawing conclusions from your data. But this part, you don't necessarily have to answer the research question yet. But if you have a graph and it's showing you that there is, here's X and here's Y, that's, here's the data, and here's your trend line, right? Well, from that, you could probably go ahead and say, well, as X increases, Y increases, yada, yada, yada. From this one, it looks like it's a linear relationship. If you've taken the time to do a trend line equation, which you should, you could state the slope. So linear relationship, the slope equals this. You could mention the R squared value at this point, which you get. You mention it in terms of how closely your data matches the trend line. And things like that. So this is where you're discussing just the simple interpretation of the data, that this appears to affect this in this way, linear or not, actually stating some values that, the way that they change, the way that they affect each other is a value of 2, is a value of 1, this per this. R squared suggests that my trend line matches the data well, or it doesn't. You could also bring up things like variability, outliers, stuff like that. So actually mentioning the values here, mentioning values that don't match the trend, mentioning trials that have lots of variability, mentioning your uncertainty here, how big it was it significant, things like that, mentioning the results. This is what you're expected to do in strand 4. And so it should be a pretty easy strand to earn marks on. And in fact, analysis in general should be a criteria that everyone can score well on if they take the time to collect enough data, process it accurately, deal with uncertainties, and then just interpret what their data shows them.